check this out. We've got something really fun today. This is so amazing, math. Oh man, again? 8.4, derivatives of logarithmic functions. We're first going to find the derivative of the natural log of x. So we're going to set up our equation here, y equals the natural log of x, and then we're going to rewrite it. And we're going to reduce it to a previously solved problem. See, here's the base is e, and here's the exponent, and that equals x. And now we're going to go through this equation here using implicit differentiation. So we'll take the derivative of both sides here, and on the left we get the derivative of e to the power of y is just e to the power of y times the derivative of the exponent, which is the derivative of y with respect to x. On the right side, we have the derivative of x with respect to x, that's just 1. So this is what we're looking for right here, the derivative of y. So we're going to isolate that by dividing both sides of the equation by e to the power of y. So we get this here, and we don't really want y in our derivative. So we're going to sub back in the original equation here. So instead of e to the power of y, it's just e to the power of the natural log of x. And e to the power of the natural log, well, those things cancel, and we're just left with 1 over x. So the derivative of the natural log of x is 1 over x. And if we had a composite function, like the natural log of some function here, then we would get the derivative of that would be 1 over f of x times the derivative of f of x. Find these derivatives. For the first one here, we'll need the product rule. So the derivative of x cubed times the natural log of x plus x cubed times the derivative of the natural log of x is 1 over x. So 3x squared times the natural log of x plus x squared. For the next one, we're going to need the chain rule here. So y prime is equal to, first we'll take the derivative of the natural log, which is 1 over whatever was inside the natural log function, so tan 2x. Then we'll take the derivative of tan 2x, and that would be secant squared 2x. Then we'll take the derivative of the 2x, and we'll get 2. We can clean this up a bit, so put the 2 here in the numerator, and in the denominator I've got sine 2x, and I've got cos that would appear in the numerator, except I'll use the secant to cancel out that cos. So I'll be left with sine 2x cos 2x. And that's pretty good. If I wanted to do something that's neat here, I could, if I just had a 2 in the denominator here, so I'll multiply by 2, numerator and denominator, then this is actually sine's double angle identity. So I could also write this like 4 and sine 4x. Okay, the derivative of the natural log of that quadratic, so that would be 1 over the quadratic, and then the derivative of the quadratic would be 2x minus 4. And in this case, I'd probably want to factor it just to see if I can cancel anything out, numerator and denominator. So 2 and x minus 2. And x minus 4. So I'm not able to cancel anything out. But there's my derivative. Differentiate these equations. Now for the first one, we notice that the base here is not e. So we can't just take the derivative yet as it stands, but we can change this around so that we can use the natural log. So first we'll divide both sides by x to get rid of it on this side. Y divided by x equals 6 to the power of sine x. Then to get this sine x down out of the exponent position, we'll take the natural log of both sides here. So that means we'll get the natural log of y over x, and that will equal sine x times the natural log of 6. Now we can use our log laws to split this one up. So we'll get the natural log of y minus the natural log of x. And now we can take the derivative of this equation here. So the natural log of y is 1 over y times the derivative of y, we'll call that y prime, minus the natural log of x is 1 over x. The derivative of sine x is cos x, and the natural log of 6 is a constant. So we just tack it on the end. We don't need to worry about taking the derivative of that or using the product rule. It's just a constant. And now we want to solve for y prime. So let's say add this onto the other side. Y prime equals cos x, x times the natural log of 6 plus 1 over x. And we also want to get rid of this 1 over y, so we're going to multiply both sides by y to get rid of that. So I'll just put this in brackets for a sec. And y, if you remember here, is equal to x times 6 to the power of sine x. And I could multiply that in. Maybe it would be clearer. So get an x, and then a 6 to the sine x, and then a natural log of 6, and then a cos x, okay, all in the first term there, and then plus the x and the 1 over x cancel, so we'll just be left with 6 to the power of sine x. So here is our answer for that pretty complicated derivative. And now the absolute value. I know how you absolutely love these questions. So we're going to rewrite this into a piecewise, the natural log of x, and that'll be when x is already positive. Don't need to worry about that. And the natural log of negative x, when x is negative, then we'll multiply by that negative to make it positive. And of course, the argument of a log can't equal 0, so we don't have either of these equaling 0. Now we'll take the derivative of these individually, so the derivative of the natural log of x is just 1 over x with the same domain. And the derivative of this one is, I'll just do it right here maybe. So 1 over negative x, and then times the derivative of negative x is negative 1. And then the negatives cancel. So what we're actually left with is the same thing here, 1 over x. Now that we've done the derivative of the natural log of x, we're ready to go back and do the derivative of an exponential function that has any real base. So we're going to start off with this. We know that e to the power of the natural log of b is just b. Okay, so using this, we're going to determine the derivative of b, any real number here, to the power of x. That's our mission. So the derivative with respect to x is equal to, and we're going to work with this one here because it has the natural log that we know about. So we're going to sub out b with e to the power of the natural log of b, and see that x exponent there is out here. And We just multiply those two together there. The x is not in the natural log function, it's being multiplied. And then we take the derivative of e to the natural log b times x. So here it is, it's the same thing, e to the natural log b times x, and then we do the derivative of the exponent. So that's what I've written here. And this is doable because we know what to do here. Okay, so the derivative of the natural log of b times x is just the natural log of b, because that's a constant and the derivative of x is 1. So the derivative of b to the power of x is just b to the power of x times the natural log of b. It gets a bit longer if we have to use the chain rule. So if we have b to the power of f of x, then the derivative is b to the power of f of x times the natural log of b times the derivative of f of x. Let's differentiate these equations. So let's just say y prime is equal to 5 to the power of x times the natural log of 5. Y prime is equal to 4 to the power of x squared times the natural log of the base, which is the natural log of 4, times the derivative of the exponent, which is 2x. And y prime here is equal to, now we need the product rule first, so derivative of x is 1 times this plus, leave the x alone, the derivative of this is just 6 sine x times the natural log of 6 times the derivative of sine, which is cos. Now hopefully this looks familiar. This is actually the question that we did earlier, and you can see how easy that got now that we know the derivative of any exponential function with any base. So that question is this one that took this long doing it the other way. Now we're ready to take the derivative of any logarithm. So here we'll set up our function like this, y equals log base b, any real base here, positive base. And we can rewrite this into exponential form to take our derivative. So the derivative of b to the y we know is b to the y times the natural log of b times y prime, and the derivative of x is just equal to 1. Solve this for y prime, we get that it's 1 over b to the power of y times the natural log of b, and b to the power of y is just x. Now you might be thinking, hey, is this something else that we're doing? Like what if b is equal to b equals e? E being the constant here. Is this something different? Now we would get the derivative of the natural log of x is equal to 1 over x natural log of the base, which is e. So the natural log of e is just 1. So see, this still follows what we were doing before. Okay, and if you need to use the chain rule, this is how it will look. If you have the log base b of some function f of x, then it's 1 over that function times the natural log of the base, and then you'd need to do the derivative of the function. Differentiate these equations. So y prime is equal to 1 over x times the natural log of 5. This one here, y prime is equal to 1 over x cubed times the natural log of 10 times the derivative of x cubed. Now we can simplify the numerator and the denominator here, so we can get 3 over x times the natural log of 10. Now you may have been looking at that exponent of 3 and thinking, hey, with our log laws, we can move that down and make that a coefficient. So if we did that, then this would be our equation. And then when we did the derivative, the 3 would just be a constant. And we would have the derivative of log x, which is x, natural log of the base, which would be 10. And you see we end up with the same answer here. Find the maximum of this function f of x. So we're going to do that by taking the derivative, and we'll do the quotient rule. So f prime of x is equal to the derivative of the natural log of x times the denominator minus the derivative of the denominator is 1 minus, so just minus the natural log of x, all over x squared. Now we see we have a non-permissible value of 0 here, but given that we have a natural log function, x has to be greater than 0 anyways. So we don't need to worry about that. So, and also there's an x in the denominator up here as well. So we can now set this equal to 0 and solve. This will just be 1 minus natural log of x. We can multiply both sides by x squared and get rid of that. And so we're just left with this numerator here, 1 equals the natural log of x. Now, when does the natural log of x equal 1? That'd be like, we could rewrite this into exponential form. E to the power of 1 equals x. And that's just e equals x. So let's put this on a number line and use our first derivative test to just double check that this value here that we found is indeed a maximum. So put 1 here, put e here, and f prime at, we need some value to test at, so probably 1 would be convenient. If we put 1 into our derivative, 1 minus the natural log of 1 would be 0 all over 1 squared, which would be 1. So it's definitely increasing before this x equals e. Let's test another value. Remember, e is 2.7 approximately, so we need another value here. And if I'm looking at my equation though that I'm putting in, I don't want whole numbers here, so actually try, how about e squared? Because that way if I put an e squared in here, this will just equal 2. So I have 1 minus 2 is negative 1, and in the denominator, e to the power of 4, which I don't know what that is exactly, but I do know that this derivative is negative overall. So we're decreasing after this point. So therefore, f at e is a maximum. And it says find the maximum, so let's find the actual value. So f at e is equal to, put e in here, that's just 1, and 1 over e. So 1 over e is our maximum. So now you can take the derivative of any log function and any exponential function. Here's some questions from the textbook. Give them a try. See if you know what you're doing.